Today we are going to continue to learn a new chapter, chapter 5. Chapter 5 is on frequency domain analysis of systems of linear time-invariant system. Last chapter, chapter 4, we learned frequency domain analysis of signals, Sn. Today we are going to do with Hn, which is the impulse response that represents the system. So we are going to see how does that look like in the frequency domain. So for the lecture today, we are going to cover frequency domain characteristic of LTI systems and frequency response of LTI systems. Next class, we will have time to talk about correlation functions and the spectrum at the output of LTI systems. So here we are all dealing with the linear time-invariant system. This is important to us, linear time-invariant system. We want to have a linear time-invariant system because we are using this convolution to represent the system, Hn convolved with Xn, or Xn convolved with Hn. The condition for this to be true, to be valid, is that I have to have a LTI system. And as we said, LTI system is mathematically tractable. We like to use that and easy to represent using many mathematical formulas. And also a lot of system, if it's nonlinear, if it's time varying, we can always break that into small pieces. Those pieces of systems, that will be an LTI system. For the frequency domain characteristic of LTI systems, first we look at a system response to a very simple signal, elementary signal, which we choose here is a sinusoidal signal. So it only has one frequency. Now, sinusoidal signal can be represented as a cosine 2 pi ft or sine 2 pi ft. Or in our case, we are using a complex exponential to represent that. So it's e to the power j 2 pi ft, where f is this one frequency. It's a pure sine wave, so I only have one frequency. And then if I look that into discretized signal, so it will be j 2 pi, frequency is f, and t becomes nt of s, which is the sampling frequency. And that is my signal, say x and ts. With understanding that the sampling period is implied, we can also write that as a discrete signal in the form e to the power j 2 pi fn. Okay, so that's the signal we are going to excite the system, input to the system. So the LTI system to a signal, to an arbitrary signal, is written in this convolution form. The condition again is the LTI system, then I can use convolution. So convolution, if I'm writing into its original definition form, is this, it's a sum hk times x n minus k. So we have one of the part, there are two parts. One part is time reversal, is negative k. Then I have a time index n here and here. So that's a convolution. Now, if my input excitation is a complex exponential, as we see here, we have a pure sine wave in my complex format using this. So here is my signal. That's e to the power j omega n. And with some amplitude, we call it amplitude a. Now a can be a real number. A also can be a complex number. Right? A complex, if a is a complex number, simply meaning that I have I not only have this amplitude, I also have a phase term, e to the power j, the angle of xn, for example, the angle of xn. And then this is, angle of a is a constant. So angle of a is just the phase. So you can add this phase as initial phase onto a term here. The response to this complex exponential to the system, we plug in this as my x. So plug in, we got the bottom equation. So we have a convolution sum hk times a times e to the power j omega and subtract k. Then after some sort out these orders, in the bracket, we have here summation hk times e to the power negative j omega k, and then a constant a here, and then I have another exponential term at the very right side. It's e to the power j omega n. You rewrite this this line here. So that's exponential. It's a pure sine wave, sinusoidal wave going through the system. It looks like that. Now I define this part as h omega. So it's written here. Define that as h omega. Because when we observe that, I find out this is just a regular format for Fourier transform. Fourier transform on signal hk, right? K is just a time index. If I write it in this way, if I write out this Fourier pair, it is implied that I have a condition, which is this k is absolutely summable. Right? K is from infinity to infinity. Only at that time, capital H is finite, and it converges. I get this out. So what we are doing here, this condition is my circle is in the region of convergence. Then I can simplify my equation. The output signal yn is a times capital H, and times what's left is e power j omega n. The output is also a sinusoidal signal with a frequency of omega, which is in here. It's exponential e to the power j omega n. My system here is LTI system. Input xn is a sinusoidal function with only one frequency omega. Output is here, yn, represent here. So the output is also the same sinusoidal function with the same frequency. The only difference is that this sinusoidal function or the sinusoidal signal has some gain, which is represented by capital H. Now, capital H has nothing to do with n. It's just one constant, right? It's just one number. Once this frequency is determined, if my input is a frequency of 100 hertz, then output is also a sinusoid with a frequency of 100 hertz. But the only difference is I have H100, which is one value. That's the gain. So we call that xn equals to this exponential function is an eigenfunction of the system. Eigenfunction meaning that it goes through the system, this same function will come out. Same thing. That's the eigenfunction will go through the system. The only difference is, of course, that I have this amplitude here, this gain here. And this gain, Hn, is the corresponding eigenvalue of the system. I have the system which is, say, lambda, if this is a y equal to that. If this is a vector, this is a vector. So that's the eigenfunction or eigenvector. Eigenfunction, they have the same, it's the same format. Eigenvector, they are in the same direction in the high dimensional space. Then I have this simple one constant, that is the eigenvalue. So if you picture that in the Hilbert space, so X is a vector. Now Y is also a vector. That's the same direction. Y is also a vector. The only difference here is that I have this gain of lambda. So you multiply by lambda, which is the eigenvalue. And here is the all the functions. So we have that. Keep that in mind. So we have something, it says, if I have a sinusoidal signal going through an LTI system, the frequency component doesn't change. I will still have the same frequency sinusoidal signal at the output. The only difference is this amplitude of this sinusoidal function will change by some gain. But there's no way for me to generate some additional frequency. If my input is 100 Hertz, there's no way for me to find a 200 Hertz signal at the output or 50 Hertz signal at the output, as long as my system is an LTI system. So we know capital H omega is the Fourier transform of signal h, little h. It follows that h omega is a periodic function with period 2 pi. Why? Because hk is a discretized signal with a index. K is an integer, time index. We are using this Fourier transform for discrete time signal and can be written here in the box. So the first one, this is the Fourier transform. That's a direct equation. This is the inverse transform, which we know all these little h can be written using this formula. H omega is a continuous variable, and omega has a period of 2 pi. Therefore, what we do is integration over a window of 2 pi times e to the positive j omega k, d omega, and then divide by the window size. So we got this inverse Fourier transform. That's how we calculate capital H and a little h that represent the system. If hk is real valued impulse response, in practice, every system that you store the parameters, it's real. Right? If hk is real value impulse response, then we have these. Then the system response, the real part, system response, the real part is even symmetric, and the imaginary part is odd symmetric around origin. Well, how to prove that? Very simple, as we said before. What we are going to do is we are going to use the definition equation on the previous page for Fourier transform, and you can easily find these two if hk is real. We also find out if I'm writing this onto a polar form, then the amplitude is even symmetric. The phase angle is all symmetric. This is easy to do because we know that this amplitude, if I'm writing that into real part, imaginary part, that will be the real part square plus imaginary part square, and then take square root. And then the angle of h omega is equal to arctangent hi over hr. Okay, and therefore we can easily to prove and to follow these symmetric properties, we can get that. Now let's look at a system response to any aperiodic input signals. So previously, we are dealing with a very special case. It's just a sinusoidal function. It's an exponential. So it is a periodic signal, therefore, the format I'm using is the Fourier transform format we are using. It's very simple. Then, if I am dealing with a periodic signal, other periodic signal, I can always decompose that into a group of sine waves. Now, if I'm dealing with aperiodic signals, any arbitrary input signal, xn, however it's discretized, xn, the analysis is straightforward because we know aperiodic signal is that we can think that this period of this signal is infinity or approaching infinity, I should say. In the frequency domain, it's aperiodic. Therefore, in the frequency domain, I will have the very first discussion is that we just have one spark. That is a one pure sine wave. And if it's periodic, then we will have something that's discretized. If it's aperiodic, then the frequency domain is I have infinitesimal space between all these frequencies, and eventually it connected together. So I have a continuous form. So the same thing for the formula, they are all the same. I still have a convolution in the time domain. So the LTI system, if I'm writing into the frequency domain, becomes a product. Y omega equals to capital H times capital X. Now X omega again at this time I know capital X omega is something that's continuous in frequency omega. Once we got that, so we can find out the amplitude of the output is the amplitude of the system times the amplitude of the input signal. The phase of the output is the phase of the system plus the phase of the input signal. This is because, well, you have two parts. It's H omega amplitude, and the phase is right here, e to the power j omega h, if I'm doing it. Therefore, for the phase, same thing using the product, then the phase is an addition of that. So from these two, we find out, well, if I'm trying to check out the output signal, what we need to do is we have the input signal. Let's say I have a filter. This filter is ideal. The system, I call that a filter because it's ideal. This is my H omega. H omega is a bandpass filter. So it's a square wave from frequency F1 to F2. So this is absolute value, absolute value. Therefore, the output signal, Y, simply is a product of these two. So I'm only going to take this middle part from here to here, from F1 to F2. This is my Y omega, Y, capital Y omega. And we are all talking about absolute value here. This is we can do with a very simple product. Now, if you want to check with the phase is actually is a sum of the phase of this signal and this signal. So we are writing out this equation for LTI system. In the frequency domain, it's a very simple product. And now we know for a block diagram, LTI system in the middle, it can be represented using the impulse response or system response. And then the input can be any arbitrary signal, xn. We can also write it into the frequency domain, capital X omega. If xn is an aperiodic signal, then x omega is a continuous function. The output signal is using this convolution to represent yn, or we are using a product in the frequency domain, give me capital Y omega. So for the system, we observe that the output of linear time-invariant system cannot contain frequency components that are not contained in the input signal. Okay, so we have here this input signal x omega here. And then you have Y omega, this omega is omega here. Then the output signal will have exactly the frequency component of the input signal if my system is an LTI system, right? This is coming from our first discussion using the sine wave, because the LTI system cannot change your frequency. Whatever frequency you have at the input, I'll give you the frequency at the output. So same thing as you have a bunch of frequencies of input signal, I'll have those same span of frequency in the output signal, but I can change those amplitude. So what I said is that if my input signal H omega, let's see, I have a frequency not only here. If I have those, say I have those three frequencies, then at the output, Y omega, I also have those three frequencies. However, those three frequencies can have different amplitude because it will be multiplied by this H omega. Now, if my input signal is continuous, let's say from here to here, the output is also from here to here, but it can be of any other shape. And how is this shape formed is because I multiply by this capital H omega. In other words, it takes either a linear time-variant system or a nonlinear system to create frequency components that are not necessarily contained in the input signal. So if you want to generate something signal with frequency not in the input, then you have to using a linear time invariant system or a nonlinear system. What kind of system is that? That I will generate some output which is not in the input signal. A modulator may be an example, or upconversion. So for the system itself, what you want to do is you want to convert, let's say, a DC signal, a baseband signal, close to DC, to a carrier frequency. So you completely change the frequency. Therefore, we know the system itself, either it's a linear time invariant system or a nonlinear system, if it's a modulator or upconverter. So we got this response to the input signal, and very easy we can generate that. I can put a square, absolute value square on both sides. So absolute value, when you do this, you can put it into those two parts. So I put a square here and a square here. Now, capital Y square, that's the spectrum of the output signal. Capital X square is a spectrum of the input signal. If the signal itself represented in the frequency domain can be complex, in general, it's a complex value, then this equals to X omega times X omega conjugate. And this is the spectrum of the signal, So the spectrum of the input and the spectrum of the output is related by H omega absolute value square. So this is still the gain or the filter gain. If you think the system as a filter, it's a filter gain. I call that a gain because you are using absolute value square. Basically, this is equal to H omega times H omega conjugate. What we discard here is the phase information, is the phase of my system. I don't need that because I'm considering the power spectrum or the energy spectrum. So I'm not caring about the phase. I only care about the amplitude. So indeed, I lose some information. I only have the absolute value of H. So let's look at frequency response of a general LTI system. We want to focus on determining the frequency response of LTI system, and then this LTI system can be represented with a rational system function. Now, what is rational system function? That is a fraction, right? If you remember before, the system HZ, rational is we have a BZ over AZ, where here BZ is a polynomial as a function of z to the power -1. AZ is also polynomial. It's a function of z to the power -1. And then I can write this into this rational format. And then this LTI system is a rational system. Recall that this class of LTI system is described in the time domain by a constant coefficient difference equation. So the good thing about that is when we have this polynomial, you can easily put it into a difference equation with all these power terms z to the power -k. That is the signal with a delay of k, which also means that it will be easy to implement, right? Because the difference equation is, we know that's the weighted sum of those delayed elements. So if the system function hz converge on the unit circle, we can obtain the frequency response of the system by evaluating hz on the unit circle. As we have said that, what does that mean? Well, hz has the unit circle, it converges on the unit circle. That simply meaning that the Fourier transform exists, and simply means that Hn is absolutely, not square. This is absolutely summable, right? N from -infinity to infinity. Now how to see that is because we neglect a term. Here's e to the power -j omega n. Put it absolute. That's my that's my Fourier transform Z transform. So if you evaluate on unit circle, then this becomes 1. So I got exactly here. H omega is hz evaluated on the unit circle. So we have here is equal to that. And again, that's on the unit circle. Therefore, that's a z equals to e to the j omega. So it's putting right here. And then we know because this is how we bridge Z transform with the Fourier transform. No wonder that this is also give us the Fourier transform format. If hz is a rational function, as we said, if it's a rational function, then I can write this into this format. Now, where does this come from? Well, it comes from the rational function of hz, when hz is bz over az. As we said, this is a polynomial on the numerator, which is with coefficients b sub k, and z to the power negative k. Okay, and k is from 0 to m. On the denominator, we have 1 plus sigma k from 1 to n, a sub k times z to the power negative k. So what's the order of this system? I'm putting it 1 here is simply that we define a0 is 1. It's normalized to 1. So if you writing a0, you can also write the denominator as a sum k from 0 to n, everything. What's the order of this system? The order is n, right? The order is n. Its order is looking at the feedback, looking at the depth of feedback. In this case, is looking at here the denominator. Denominator with k from 1 to n, and you need to multiply this. That is yz over xz. You multiply denominator to yz, and xz multiply to the numerator. Therefore, this part on the denominator that's the coefficient of my feedbacks of y's. So that's the depth of feedback, which is n. Okay, anyways, so here I plug in that into this equation. Then we can generate this. We can generate this. So write out this as a rational system function. So h omega is written in this format. Then the polynomial, we can do a factorization into a product on the numerator and a product on the denominator. And here, all these z sub k's are the zeros. All these p sub k's are the poles. The same as we defined 0 in the poles for a z transform. Okay. Now, if I am writing out h omega conjugate, the entire thing conjugate, then what I have here is you take the entire thing. If this is putting a conjugate here, you take the entire thing conjugate. Therefore, you put in now z, p, those are the values that can be complex. So if you put this in, that will move here in here. That's a complex here, complex here. Now also e to the power negative j omega, that's a complex value. So when you do conjugate, you put a positive sign here. Therefore, we got this line here. We got this line here. That's the h omega conjugate. H omega conjugate. And also, if I'm writing this entire thing into this format, if I am using z equals to e to the j omega, I can plug this in, right? Plug this in. It's easy putting here, putting here. Then for the original thing, then I need to write out it's h omega, then z to the power negative 1 conjugate. Kind of, let me just put in a negative conjugate. It's z to the power negative 1 and conjugate. Like this. Conjugate to the power negative 1. This is if I am plugging, if I erase that, if I'm plugging my original hz, that should be equal to a sum, and a bk. What we have here is z to the power negative 1, and here is a sum of 8k's z to the power negative negative k here. Then if you are looking into this format, as if I am changing this z to the power negative k now becomes a z conjugate k. Okay. So I'm using z conjugate negative 1 and put into this format. So that is equal to this, When Hn is real, equivalently, in this case, Hn can be represented, the system can be represented using a rational format with all the coefficients a subcase and b subcase. Then those coefficients a and b are real. We have complex variable poles and zeros occur in complex conjugate pairs. The same as we discussed before. If those coefficients are real, then the zero and the poles, either they are real, or if they are complex, I must have another complex conjugate pairs. This thing is equal to this complex, and then we can plug in this z conjugate, so z to the power negative 1, and that will be equal to h conjugate as a function of z conjugate to the power negative 1. Okay. And then consequently, if you plug in my h, now we know this is represent, plug in the frequency omega, this represent that. And here, this is z to the power negative 1 is negative omega. And because z is equal to e to the power j omega, so z negative 1, I'm putting negative here. So as if I'm using negative omega. So I will have that. I'll have that. Which is what we discussed before. If Hn is real, and then I have H omega has its real part even symmetric, has its imaginary part odd symmetric. So this entire thing, we call that a conjugate symmetric. It's like that. And then the absolute value of H square is equal to H times H conjugate. And we also know this term is equal to H negative omega. So I can write it in this format. And that is equal to, because now this part is my H omega conjugate. We also know that we can represent that using Z, which is Z conjugate to the power negative 1. Okay. Equal to that. And this part is equal to H Z to the power negative 1, according to the line here. Therefore, I can write it out as here, Hz times H as a function of Z to the power negative 1, when Z is evaluated on a unit circle. So this is the spectrum, if you like. It's a spectrum of the system. H absolute value square can be written as 4. Okay. Hz times Hz to the power negative 1 is the Z transform of RHH. What does that mean? Well, this is the autocorrelation of H and H. And this part is here, is my power spectrum, H. Okay. We already know that this is my SHH. Then this part, I know it's my power spectrum of H, if you like, that is equal to this. This and then this, that's a Fourier transform pair or Z transform pair, same thing if this is HZ. So we have here, this is represented Z here, okay? And that is the Z transform of the autocorrelation function. We have already used that when we are dealing with any signal X, right? Here, we only changed X to little h. So we think this system is represented by a discrete signal Hn. Then we can talk about similarly the autocorrelation of the system. But system itself, there's no autocorrelation. but simply meaning that Hn convolved with H negative n. We got this autocorrelation of H. And then its Fourier transform, or the Z transform, and becomes this quantity. And it also follows that the H omega square, H omega absolute value square is the Fourier transform of the autocorrelation of the system. So we can discuss all these, we extend it to discuss all these on the system of the autocorrelation and the spectrum. We used that before dealing with signals. So now we can also talking in the format of autocorrelation of a system, linear time-invariant system, H. So the system, this is LTI system, represented with Hn. Input signal is X, output signal is Y. We know that this is a convolution with H convolved with X. We can prove that this is also true if my input becomes the autocorrelation R XX of N. N is a time index. So actually from autocorrelation, we know N is, we used L before. It's a time lag between those two X signals. They are autocorrelate with itself. But we know it's a time index, so we're putting N as well. So if this goes through the system, what will be the output? Well, the output is the cross correlation between the output signal Y and the input signal X. Okay, we have did this before. If you remember, we did this before. So this is the line here. That's also a convolution. Now, if my system here, we are talking about the system also represented by autocorrelation of H and H. Then if the input is the autocorrelation of the signal X, then the output is the autocorrelation of the original output signal Y. So R, Y, Y, N. So that's the first line we have here. Using the Z transform, convolution becomes a product. Therefore, the spectrum of the input times the spectrum of the system, it becomes the spectrum of the output signal. The spectrum of the input multiplied by H, which is system response, it becomes the cross spectrum. We call it cross spectrum, but it's not a, we don't really have a physical meaning for the spectrum. Mathematically, we have something to, we can write as what is capital S sub Yx. So we call it cross spectrum of signal Y and X in this format. Substitute Z with that, with e to the power omega j. So we evaluate only on the unit circle. Therefore, we have all these that's coming from the Z transform. Now we have all these in the frequency domain. The same thing, this is the spectrum. Spectrum, it's a function of omega. Right? This is spectrum in frequency that has a physical meaning. And then we also can talking about in this term that is related. And in frequency domain, it's very simple because it's a product. The energy in the output signal is, now once you got the spectrum, this is a spectrum of the output signal, then what we can do is we just integrate them, d omega, over one period of 2 pi. So if this output signal is periodic of 2 pi, which means the signal y in is discretized, and then I have this periodicity in capital Y. Integrate over one period of 2 pi divided by 2 pi, and that's my energy in the input signal, at the output signal. And that is also equal to this autocorrelation of Y and Y when those signals align exactly on top of each other. So the lag is 0, which makes sense. So we got a signal Y, let's say from here to here, and it takes the same signal Y, okay, with the lag is 0, so you line on each other, and they multiply each point, and add them together. Of course, you got the energy. That is when the lag is equal to 0. And we can also show that using the inverse Fourier transform. All we have here is you put an e to the power positive j omega n. And when n is equal to 0, so this term goes away, right? This putting here. That's the inverse Fourier transform. And because you don't have that, so n is equal to 0. So you plug in n equal to 0. We got that. That's also coming from this power spectrum, or energy spectrum in this case, and this autocorrelation function. That's a Fourier transform pair. Okay, we can also write this in this format. If I'm using the spectrum of the input signal x, and then I just have this term here.